Welcome to a course devoted to the reality of global warming and the role of carbon emissions to addressing new policies that intend to reduce the built environment's carbon emissions, emphasis on intend, and to do so effectively, which means in a timely manner. In other words, to reduce upfront embodied emissions is the key. California was the first state to initiate embodied carbon policy and legislation, the Buy Clean California Act of 2017. New York State's Climate Act, which included emissions associated with manufacturing and the building sector, became law in 2019. In the early days of my engineering career, designing sensors for defense projects and the space shuttle program, the phrase embodied carbon was not even in the English lexicon. Yet today, it plays a pivotal role in sustainable design, a pivotal role in global warming. Nonetheless, there are gaps between design strategies and their actual impact on carbon emissions. As a project develops and design strategies evolve, gaps between assessments and real performance widen. Now, these are not my words. I'm quoting SOM's webpage for whole life carbon. You can take a look yourself, which speaks of a gap up to 5 times more energy use or carbon emissions between the predicted and actual values. So let's address some issues that create these gaps by starting with our first objective, understanding the relationship between embodied emissions and the acceleration of global warming. Embodied carbon and embodied emissions might be the most poorly named concepts in the global warming vocabulary. There's nothing embodied about embodied emissions. By the time we refer to them, they've already been released. They do not exist in the material or the product in question. This beautiful sky is what embodied emissions look like, residing in the atmosphere as atmospheric carbon, not visible to the eye. They will remain there for hundreds of years, multiplying the greenhouse gas effect. Water vapor is also a greenhouse gas. Water vapor and stratiform clouds contribute nearly 3/4 of the greenhouse gas re-radiation. Carbon dioxide is just 20% of the greenhouse gas mix. Though only 20% of the mix, carbon dioxide's greenhousing effect controls 80% of the impact. Heat re-radiation from atmospheric CO2 increases air temperature, which in turn influences the air's moisture content. But unlike water vapor, CO2 neither condenses nor precipitates from the atmosphere. It stays there, re-radiating heat and enabling higher levels of water vapor, which do so as well. This nebulous thing called embodied carbon is one of the few warming accelerants that we can minimize within this decade, something that all of us can do. What are the embodied emissions associated with building design? That depends on your perspective. To some, it's manufacturing emissions, the emissions associated with producing a product. That means from raw material mining through production and packaging and everything in between, from cradle to the shipping dock. To others, it includes transportation to the construction site, or maybe installation or maintenance or repair or refurbishment or disassembly and disposal or preparation for eventual reuse. Is embodied carbon important? The Inflation Reduction Act thinks so. It put $4.5 billion on the table for low-carbon construction materials. The Buy Clean California Act and the Federal Buy Clean Initiative think so as well. With 2030 targets a mere 5 years away and a climate crisis brewing like the wildfires in LA, minimizing emissions upfront is crucial to maintain a 1.5 degree target. But why is this crucial? Perhaps because embodied emissions are immediate and unrecoverable. Some might ask, with wind and solar and electrification on the rise, why this sudden emphasis on upfront emissions? To answer that question, let's cut to the chase. Let's connect a few dots and look at carbon dioxide and the warming timeline. The blue line here traces the increasing concentration of atmospheric carbon dioxide from pre-industrial through 2023 in parts per million, ppm. In 1910, for the first time in over 300,000 years, the concentration of atmospheric carbon exceeded 300 parts per million, increasing to 389 parts per million in 2010. 89 parts per million over 100 years. The rate of increase since January 2000 was 2.5 times that, 56 parts per million in only 25 years, to a global average of 425 parts per million for the first week of 2025. Unfortunately, atmospheric carbon is the factor that induces global warming. For the 2,000 years prior to 1900, the average global temperature stayed within plus or minus 1/4 degree Celsius. Since the early 1900s, it has increased more than 1.3 degrees C. That's the red line here. Notice the sharp rise since 1970. According to NOAA, the National Oceanic and Atmospheric Administration, 2023 was the warmest year since global records began in 1850. The average global surface temperature for 2023 was 1.35 degrees C above pre-industrial, the Paris Agreement baseline. I created this graph last March for my keynote at LA's 1.5C symposium. That was in April 2024. This is what it looks like now, a bit shocking. October 2024 hit 1.65 degrees C above pre-industrial. It was the 15th month in a 16-month period to exceed 1.5 degrees Celsius, bringing the 12-month running average to 1.62 degrees C. When the final stats are in, 2024 is expected to hit another record and the first year to be above 1.5 C. Temperature increases are nearly linear now with the increase in atmospheric carbon. The concentration of atmospheric carbon is driven by carbon dioxide emissions released from fossil fuels and industrial production. That's the black line on this graph, in billions of metric tons per year, gigatons. Every ton of CO2 emissions adds to global warming. The red circle here reveals the reduction in annual emissions in 2020 due to the COVID shutdown. The dip in the black graph is considerable. A reduction of more than 2 billion tons of carbon emissions for the year. But notice the blue line, the level of atmospheric CO2. It continued to climb. Why? Because CO2 emissions remain in the atmosphere. They are not reduced as emissions decrease. New emissions are additive. They will remain in the atmosphere for centuries. To flatten the growth rate of atmospheric carbon emissions, we must reduce emissions now, annually. As you can see from this graph, annual emissions have already returned to their pre-COVID level and continue to increase. These blunt covers of two emissions reports express our current reality. On the left, you have the International Energy Agency's emissions report, which announces a new record high, and then it queries, is there a light at the end of the tunnel? The UN report on the right gets right to the point. No more hot air, please, and notes the massive gap between rhetoric and reality. We may be well on the way to decarbonize our energy supply, but our demand is increasing faster than decarbonization with no net gain. This drill on climate science is to make a single point: the urgency of tackling upfront emissions. What we spew into the atmosphere today and tomorrow will increase global warming immediately. This is why upfront embodied emissions are so egregious. As much as 70% of the carbon emissions attributed to new buildings from now through 2030 will come from embodied carbon. Waiting for the 2030s or for future decarbonization is wishful thinking. This brings us to our second objective: the foundational nature of embodied carbon to the veracity of sustainable design. It comes down to efficacy, the effectiveness of our attempt to design sustainably, to take stock of reality. So how are we doing? Are we minimizing greenhouse gas emissions in a timely manner? Does our progress reflect building design? Or is it coming from equipment and appliance efficiencies? Or is it primarily from energy decarbonization? Is our current approach to sustainable design enough to thwart global warming? Let's turn the calendar back to 2018. I was researching my book about embodied carbon, Thwart Climate Change Now. That December, as one of AIA's Committee on the Environment's 10,000 members, I received an email, a post to Coates' website. I remember it to this day. It began, "Happy holidays. This is big." It explained that amid sobering projections about climate change, there was actually some upbeat news to share. Quote, "Our hard work is having a big impact," it said. Our hard work caught my attention. It said that energy efficiency and power sector decarbonization have reduced U.S. building sector CO2 emissions by 20% below 2005 levels. This was despite adding approximately 30 billion square feet to our building stock. At first glance, I thought, wow, our work is having a big impact. Sustainable design must be working. But reading further, I realized this upbeat news, based on an Energy Information Administration report, was attributed primarily to energy efficiency and to power sector decarbonization. So what part of that was due to designing buildings? Parsing the data, the minutiae, was like opening Pandora's box. The 20% reduction was real, but had little to do with building design. The significant reductions came from replacing coal with natural gas, wind, and solar, and a notable reduction in the energy used for illumination, from compact fluorescent lighting, from the introduction of LEDs, which perhaps was the most significant contribution to lowering operating emissions since 2000. But there were other factors too. Energy demand had decreased due to mild weather and to poor economic conditions. One might say emissions declined in spite of the design of new construction. And there is something else to note here. EIA's building sector only included emissions from the residential and commercial use sectors, and only their operating emissions, such as heating, lighting, air conditioning, and electricity consumption, not embodied emissions, not from the manufacturing, the structure, construction materials, nor the fittings, fixtures, and furnishings, nor manufacturing the building systems or appliances, nor from the transportation of any of these items, nor manufacturing the construction equipment or vehicles or operating them. In other words, due to how economic sectors were categorized, the magnitude of emissions attributed to buildings was significantly higher than reported. This is what I mean by taking stock of reality, the veracity of the claims and the efficacy of the design actions. Since 2018, our understanding of sustainable design has changed. We've learned that not all carbon emissions have the same impact on the rate of global warming, that upfront embodied emissions associated with the production of construction materials accelerate global warming. They add fuel to the fire and play a defining role. Embodied carbon is the elephant in the room. It is foundational to sustainable design. Regardless of all the green certifications, fawning articles in the press, and competition award winners, we are not doing enough. Excess embodied emissions are not a necessary fact of life. Designed in by structural, material, and aesthetic decisions, they have been little more than an afterthought, some even in the name of sustainability. We need to think of sustainable design as commencing with low-carbon construction. In other words, we need to relate spatial, structural, and envelope design to material selection while cognizant of embodied carbon. The same is true for fittings, fixtures, and furnishings. To provide a little context, let's focus on a few building designs, ones that highlight what I'm talking about, the impact of embodied carbon, the upfront kind. This is the new design studio at the University of Miami School of Architecture, completed in 2018 and LEED certified. The 20,000 square foot roof with its 5,000 square foot overhang was constructed from reinforced concrete. Embodied emissions estimate at more than 100 metric tons of CO2 in addition to those from the building's concrete walls. We all know that cement is responsible for about 8% of the world's energy-related CO2 emissions. I hope architecture students learn that as well. It's not that cement concrete was used, but rather the overabundance, the quantity. What were they thinking? Should this be a model for architecture students to emulate? This 62-story residential high-rise in Miami was completed in 2019. The exoskeleton was clad with 4,800 precast glass fiber reinforced concrete panels, weighing a ton or more each. They were shipped from Dubai, 9,000 nautical miles in dozens of trips. CO2 emissions from concrete cladding might be deemed excessive by itself, especially when fabricated in Dubai or the UAE, where cement kilns are primarily heated from coal. But shipping from Dubai to Miami, adding hundreds of thousands of kilograms of additional CO2 emissions. On top of that, they required custom steel cradles for protection, adding significantly to the embodied carbon. What were they thinking? This beautifully conceived LEED Silver project with geothermal wells for heating and cooling was completed in Connecticut in 2015. They chose environmentally sustainable glulam beams for part of the structure, a great carbon sequestering choice. The LEED certification for building design and construction even noted the use of green building materials. Perhaps their point of origin was not part of the equation. These glulam beams were fabricated in Vancouver, British Columbia. The project is in Connecticut. Some of these beams, as long as 95 feet, were unsuitable for transport on winding roads. They had to be trucked by a route around the Rockies from British Columbia almost to Mexico, then up and across the United States to Connecticut. around 20 truckloads responsible perhaps for 250,000 kilograms of CO2 emissions. Even environmentally conscious design can be undone by transportation. And let's not forget the full-height glass panels. They were manufactured in Germany, then shipped to Spain to be curved before their trip to Connecticut across the Atlantic. Sustainable design? What were they thinking? This computer science building at Cornell University, my alma mater, was finished in 2014. A glass-clad structure with steel sunscreen appendages to block heat-inducing sunlight. This is the north side of the building. According to Cornell's Sustainability Office, these angular sunshades contributed to the structure's LEED Gold certification. Nonetheless, intense sunlight from the east and south necessitated additional interior pull-down screens to screen the exterior screens. That's the photo on the right. Why one would design a computer lab with floor-to-ceiling windows that admit sun and glare, I will leave to you. But it's hard to ignore the addition of steel sunscreens on the north side of a building in the northern hemisphere. Steel emissions are in the same league as cement, responsible for about 8% of global energy-related emissions. Was this just for aesthetics? In the name of sustainable design? What were they thinking? What about solar panels? The rooftop solar installations generated enough energy to justify their embodied carbon footprint. Not this one in Bronx, New York, with panels oriented to the north. Nor this one shaded by trees. These may reduce a homeowner's electric bill, but these arrays, solar arrays, have a net negative impact on global warming, probably for their first decade of operation. And this is not uncommon. Perhaps you're thinking that maybe these residential examples were installed by the homeowner. This array, however, was designed in by architects. It's in New York City's Washington Square Park amidst tall trees and tall buildings, and was installed in the name of sustainable design. And this one, in New York City, on the roof of the Borough of Manhattan Community College. 947 solar panels installed by New York Power Authority, touting a daily capacity of more than 1 megawatt hours each day. Not with this shade, it's even in their promotional photos, solar panels shaded by the building itself. This is a satellite shot for a better view. The building actually faces west to California. There are two vertical arrays which rarely see the sun. It's denoted here. This is a vertical array, and there's another one over here. They rarely see the sun, and a significant portion of the array itself is shaded by the building itself or by other buildings for many hours a day. What were they thinking? Not all rooftop solar installations justify their embodied carbon footprint. Southern regions in the United States receive sufficient irradiance, but northern states have 10 to 25% lower solar exposure. With shade from buildings or trees or poor directional alignment like these, they can actually add to global warming for a long time. For all of these projects and numerous more like them, they were thinking about fluidity of design, in some cases perhaps sustainable design. You know, the thermal mass of concrete, carbon sequestering wood construction, the benefit of sunscreens, and why not add solar panels? But they weren't thinking about embodied carbon, about upfront emissions. So let's borrow a phrase from our Homeland Security Department. If you see something, say something as early in the design process as possible before it gets baked in. When we have embodied emissions in mind, addressing excess materials and port choices and transportation emissions becomes obvious, and that's a good place to start. but weighing the potential of future operating gains against their cost in upfront emissions is critical, which brings us to the last two objectives. Buy clean policy and legislation qualified by EPDs and designing to proforma versus proformative action. New policies, legislation, and buy clean programs that incentivize or require low-carbon building materials require environmental product declarations, EPDs. This started in the U.S. with Buy Clean California and is also required for IRA funding. It's also the basis for New York State and New York City executive orders that address low-carbon construction materials, and for the many state and local policies that followed. In 2018, the Royal Institute of British Architects asserted that architects should undertake whole-life carbon assessments, including embodied carbon. And it should follow the Royal Institution of Chartered Surveyors standard of 2017, an approach being codified in Europe and gaining traction in the US and elsewhere, including the AIA's 2030 commitment. So where does this lead us in our quest to thwart the acceleration of global warming? There are three phases to the accrual of embodied emissions in a product or a building's life cycle. The first phase, from raw materials to installation, is known as the A block. Then comes the use period, the B block, maintenance, repair, and replacement, etc. Finally, this C block, end-of-life emissions, deconstruction, transportation, waste processing, and disposal. If circularity is in the discussion, there is a fourth phase, the D block, recovery and reuse. All of these are important, but our immediate goal is to reduce upfront emissions. That's the A block. What occurs past the A block, past installation, is speculative. More speculative the further out you go. Speculative about use, speculative about maintenance, repair, and replacement, especially about a building's lifetime, or whether components will be recycled or reused at all, or whether embodied carbon will even matter 40 years from now should zero carbon energy dominate the grid. Whole life cycle modeling may be pro forma, but not proformative, at least for now. Life cycle A block emissions are tangible. They're controlled in real time by your design and your procurement decisions. Focus on your A block decision making. What about circularity, the potential for reuse? Am I saying don't bother? Absolutely not. Circularity is extremely important for many reasons, even if a particular component is never reused. Designing for ease of disassembly or reprocessing is a carbon benefit, and it may be designed to minimize waste, pollution, and landfill, all environmentally beneficial. But nonetheless, having low upfront emissions is critical for circular products too. At every stage of design, we need to question the global warming potential from conceptual to structural to envelope design, to fittings and fixtures through material procurement. Whether it's material selection or substitution, structural strategies, circularity or reuse, or material conservation, your ability to predict the efficacy of your designs will rely on a few simple factors. First and foremost, how much of a product will you use? Second, what is the product's global warming potential? Its GWP, its CO2 equivalent emissions per unit of use. And third, where is it manufactured? GWP and point of manufacture can be found on a product's environmental product declaration, its EPD, if it has one. Which brings us back to the Achilles heel of low-carbon design, EPDs. Addressing material abundance or the use of long-distance shipping is obvious. but trying to compare the emissions from one design scheme to another, or comparing one vendor's products to another's, is something else. If you hope to qualify a project for Buy Clean or low carbon requirements, or for IRA funding, you must rely on construction material EPDs that qualify to the program standards. In fact, New York Executive Order 22, effective in January 2023, requires EPDs for covered products when available, for permitting new construction of 5,000 square feet or more for New York State agencies or departments under the governor's authority. Design teams must calculate embodied carbon. But while EPDs must conform to product category rules, a PCR, multiple PCRs may be issued for a given product by different groups of interested parties, and optional formats may be allowed by a single PCR. So where does this get us in our quest to actually lower upfront emissions, to be performative? This is an EPD, and it's what Tommy was referring to. This is a new one. Here are 2 pages from this recent EPD for ready-mix concrete from a plant in LA, issued just 2 weeks ago on January 10th. The mix has a compressive strength of 4,000 psi at 28 days. Now, it's important to note that this EPD was calculated using manufacturer-specific cement data, a requirement for IRA funding and many Buy Clean programs, and it gives credibility to the GWP that's actually declared. Though it's strange that in this particular EPD on page 4, it is stated in the data source section, that's right up here, that all upstream material inputs have been sourced from industry average data sets, and notes below that the cement data was reported in 2021, but this EPD was just issued in 2025. Well, perhaps page 4 is merely boilerplate. So let's take for fact that this was calculated using the manufacturer-specific cement data. This declaration is from another EPD for a 4,000 psi mix. It was issued in September 2024 from a different supplier. This is in the state of Georgia. Both EPDs were downloaded from Building Transparency's EC3 database. This one comes with a huge disclosure caveat. While the prior one was computed using manufacturer-specific cement data, this one used industry average cement data. As such, the GWP value declared on page 1 is modified by a caveat, a disclaimer right here on page 2. It states that manufacturer-specific cement impacts could result in variation of as much as 43%. In other words, the GWP declared on page 1, the 261 kilograms of CO2, might be inaccurate by 43%. A caveat like this renders an EPD meaningless. And perhaps the industry average data source noted on the prior EPD was meaningless as well. Close to 80% of New York State plants that entered or updated EPDs in Building Transparency's database in the 6 months through September submitted EPDs with such caveats. Nonetheless, to evaluate the global warming potential of any manufacturer's products for any of your projects, you must rely on its EPD and compare it to the others available, which may have its own set of issues. This is a screenshot of the find and compare function from EPDs in the EC3 tool from Building Transparency. I've selected 5 4,000 psi ready-mix concrete products specifically to demonstrate some of the potential issues that are, these are not from the same state. The green box plot on the left graphs the GWP spread for the 7,700 database EPDs in their database that met my selection criteria when I selected these 5. The 5 blue box plots to the right graph EC3's own certainty spread using their own formulation for each of my selected EPDs. So I've noted here for you in the red boxes some of these issues. 2 of the first 3 EPDs calculated their GWP using 100% supplier-specific cement data. That's this and this column. The center one used industry average data with the caveat that its impact could vary in that particular one as much as 45%. And so I noted this above the box plot in red right here. Yet EC3's algorithm assigned all 3 of the products with the same EC3 uncertainty bandwidth of plus or minus 11%, which is also here in red. EC3 tool assigned the remaining 2 EPDs in my selections, the ones on the right, a mere plus or minus 3% uncertainty, which is really fantastic. But even though the EPD with the red disclaimer, this one here, in fact, that's the one that I showed you earlier, was calculated from industry average data and had declared a 43% variation caveat. It appears that EC3's uncertainty algorithm is driven by entries to its uncertainty checkboxes for each digitized EPD. And I've placed screenshots of these checkboxes for the first and fourth EPD in this display adjacent to the box. So these were the checkboxes associated with this spread, and this is the checkboxes that were checked in the EC3 transparency tool, which gave us this bandwidth. The checkbox block on the upper left for the EPD with the supplier-specific cement data actually indicates for its supply chain entry box right here that it's 0% supply chain specific, which doesn't make any sense. Yet the block to the right for the EPD with the industry average data, that's this one here, has a data entry of 86% supply chain specific, even though it was industry average data. And perhaps that's why it was given a 3% uncertainty. To me, I don't understand. This doesn't make any sense. But I'm not an expert on EC3, and perhaps their uncertainty adjustments have nothing to do with EPD disclaimers. But for me, when a digital EPD comparison offers a suitable product with the lowest GWP and the lowest uncertainty, even though the EPD itself has a significant supplier disclaimer, I wonder, what were they thinking? Whether it's because EPDs can have caveats, or that digital databases may have entry errors, or lack data entry quality control, or quality assurance, or maybe even oversight, or have their own interpretation of uncertainty. Unfortunately, the end result is the availability, reliability, and comparability of EPD data is severely lacking. We have a long way to go. Aside from ready-mix concrete, there is a paucity of EPDs to survey and little geographic distribution. For those that exist, there lacks a single rule set to support comparisons and certainty. And nothing requires EPDs to be comparable from manufacturer to manufacturer, or even from different plants of a single supplier. The EPA is working to change that by developing a registry for low-carbon construction materials. That means IRA standards. That meets, IRA standards. Hopefully, this program will be viable, but it will take years to facilitate and gain traction. Unfortunately, we cannot rely on public policy mandates to drive changes needed. So until a sufficient supply of standardized EPDs is widely available, what can you do in the meantime to lower upfront emissions? Just meeting the proforma of new climate policies or following building codes to the letter rather than the spirit will not reduce carbon emissions soon enough to make a difference. Low carbon design will rely on your creativity and your skill sets, your design and your material choices. With time being of the essence, you need to focus on what you can control. Modeling is crucial to design decision making, from structure and envelope to environmental control systems and a host of other parameters. So how do we handle the EPD problem? Modeling and detailing are at different ends of the spectrum. That's if you model to design rather than model what you've already built. Industry or manufacturer average EPDs or database averages are sufficient for modeling design schema comparisons. Whether for the structure, envelope, or interior, a GWP estimate for modeling can be determined for most EPDs, even for those which may seem somewhat misleading. Just be sure to factor in the caveats. Comparing design approaches can be accomplished with generic information, but detailing is another matter. Ultimately, success or failure of a low-carbon project will be cast by the structural and aesthetic decisions carried out through detailing and locked in by a spec writer. And that's when emissions comparisons become critical, ultimately relying on the veracity of specific EPDs. So I will close with a few rules of thumb that can help. Rule number 1 is the easiest way to cut embodied carbon. It's a throwback to Mies. Less is more. No matter what material you select, less of it is more climate friendly. Embodied emissions come by the pound or kilogram or by the unit or square foot. For example, a 50-pound bag of cement emitted from about 40 to 45 pounds of carbon dioxide during production. Of course, material reuse or increasing a building's lifespan by renovation or adaptive reuse serves this credo as well. Rule number 2, be cautious with products processed at high temperatures. Firing ceramic, porcelain, and brick, sometimes multiple times for surface effects to create color or a shade of black, or for glazing or adds emissions. Thanks to this helpful disclosure from a brickmaker's EPD, one can see the emissions impact on an aesthetic choice. There is a 21% spread in upfront embodied emissions from color groups 1 through 10 for this supplier's EPD. Your choices matter. Rule number 3, check out a product's material content. You can't tell a book by its cover. Many construction products are a composite of materials such as for roofing and siding. The principle of mass applies here too, the mass of high GWP constituents. And of course, there is rule number 4. Whatever the product, let's not forget transportation emissions to the construction site. And all of these apply to aesthetic structural schemes, especially for tall buildings. No single form is best for all buildings. Each structural system has a specific sweet region for embodied carbon versus height. A tall building's gross floor area tends to increase linearly, but increasing column sizes and core walls to support forces above a certain height cause a structure's embodied carbon to increase exponentially. Conversely, as height is reduced toward a low rise, the curve reverses. The carbon footprint per unit of floor area increases, as the base structure's embodied carbon represents a larger share. This was modeled in a comparative analysis of embodied carbon in high-rise buildings regarding different design parameters, which was published in 2017. Selecting the structural form best tuned to the intended height can make a significant difference. But if you can only handle one of the above rules of thumb, make it rule number 1, use less. I came across an excellent report published by the World Business Council for Sustainable Development that might be of help as well. Net zero buildings halving construction emissions today. The report provides excellent strategies to reduce embodied carbon emissions. It's available for free download at wbcsd.org. I highly recommend it. For a more complete picture of the mindset we need going forward and how our love affair with all things green and sustainable got us here, my book might help as well. Thwart Climate Change Now, Reducing Embodied Carbon Brick by Brick. I wrote it to be a solutions-oriented eye-opener. It comes down to our creativity and to our personal design decisions. We must take it upon ourselves to act performatively. With approximately 120,000 registered architects in the US alone and 3.2 million estimated worldwide, you can make a huge difference. And that doesn't include interns or other design professionals and the rest of the AEC industry. This is an enormous amount of specification power, capable of minimizing upfront embodied emissions through low-carbon construction. Keep in mind that emissions from construction materials are released years before a building is occupied, years before infrastructure is used. That is why your ability to cut upfront emissions through design and by material selection matters so much, why it is so important. So let us focus on upfront emissions and let's spread the word. And please don't forget, if you see something, say something. Thank you for listening.